So I work in CETIAT, and in CETIAT we are also interested by the assessment of those low-cost particulate matter and VOC sensors. We already know demand control of ventilation using humidity sensor or CO2 sensors. That's why we wanted to focus on those new, we said new IAQ sensor. What we have seen is that since 2 years now, the number of sensors that are available for the end user is increasing, and I'm sure that for 6 months ago there's almost new sensor now. We are interested in low cost and standalone sensors that are dedicated for consumers, and they are compact and internet connected. Those sensors are measuring particulate matter and volatile organic compounds. We are interested by the assessment of the sensor regarding their sensitivity, their response time for on-site use, and also in laboratory. And in our study, we were really interested by the response of those sensors regarding the nature of pollutants, so this in size distribution, and also in case of matrix of gases for VOCs. So here are the sensors that we have tested at CETIAT. Maybe you will recognize some that have been already tested by the previous study. We chose to give results without giving the name of each sensor. It's our way to function in CETIAT, so they will be anonymous. Most of the sensors that we have bought are measuring particulate matter or particles, and also VOCs. One sensor says it measures CO2, but in fact, it does not measure CO2. It's just a transposition of its VOCs sensors into CO2 value. So before beginning the test, we wanted to know what are the information available in order to choose those sensors for the end user. And in fact, what we see for this 8 sensors is that there's very few information for the quality of measurement, and they're very heterogeneous. For example, for the sensitivity, you can see the sensor A and B, they begin their sensitivity at 0.3 micrometer, but the A is going up to 10 micrometers, the B up to 2.5, and the sensor A begins at 0.5. This will have an impact on the results, of course. Thomson and C, D, and F sensor, we don't know what is the sensitivity. Sensor are given values expressed in PM 2.5, PM 10, or they give directly the concentration in microgram per metric cube. And some sensors, they say they measure the particles in number, and then they use the transposition to convert it in microgram per metric cube. And we have some information on the uncertainties. So the A sensor says 10%. The B sensor says plus minus 4 microgram per metric cube, or plus minus 20%. The C just gives its resolution, so we can guess the uncertainty is higher. And just one sensor gives it a response time, which is very small. But we will see that further that it's not a problem, the response time. We have also noticed that it was quite difficult to connect those sensors to the internet, and as Jan just mentioned just before, some sensors do not give any value if they are not connected to internet, and if we lose internet connection, we lose all the data. And that's why in the study further you will see that for sensor we have 2 products. And for some sensors, we have only one because we were not able to connect the data or to connect the sensor or to take the data after that. So first of all, we have made some on-site measurements. It was in a house installed in the countryside of Lyon. It was not a very polluted area, so the external particles metrics were quite low. And we have made a study during 1 month. So here you have an example of the screen of the data acquisition for the sensors. And if we look at the range of the measurements for the indoor particulate matter during this 1 month, we can see that for 3 sensors, they do not have the same range. So one is beginning at almost 0 microgram per cubic meter, but 2 sensors, they begin at 5 or 10 microgram per cubic meter. This means that they will never go lower than this value. And if we see the maximum value of this range, they are quite different from each other. So now we wanted to go further, and we decided to make tests in our laboratory in order to have better improvement on our pollutant. So the test at CETIAT were in a test room of 8 cubic meter and was connected with an external supply fan with a high efficiency filter. This allowed us to clean the room between two pollutants campaign. And inside the room, we made the injection of pollutant just behind an indoor comfort fan in order to mix the air to have as most homogeneous as we can in the room. All the sensors were placed in a table in the central zone of the room, and you see there's a lot of electrical wire to connect everything, and also you can see a phone here because we could not connect to the CETIAT Wi-Fi box, so we need to go through a smartphone directly. The sensors are placed 2 by 2 in order to be sure that the place is not influencing the response of the sensor. For the particles only, we use a reference value with a contour of particle, which is TSI 3330, and it counts particle on 7 channels from 0.3 to 10 micrometer. And as it has been asked just before, yes, there's some uncertainties when coming from a number of particles to going to a mass concentration. So we use some equation with hypotheses of on the diameter of the particles, and the main hypothesis is on the density of the particle. So here for the study, we use a density of 2.8, but we really want to aware people that this might be not a density for all particles in indoor air quality. So the particle generated in our study were talcum powder, tobacco smoke, and incense smoke. Here you can see on those 2 graphs the size distribution. So a percentage per number of particles. For the incense, it's mainly very small particles. Tobacco, it's almost less than 1 micrometer. And talc powder is heavier particles. And in percentage, in mass, so the percentage is different, and we can know why. But in fact, the size distribution is not the same for those 3 kinds of pollutants. And we will see the impact on the response of the sensor. So first of all, the response to incense smoke. Here on this graph, you can see the our counter of particles in gray. So with our hypothesis on the density. And for very small particles, we see that sensor B2 gives the highest value and sensor A gives the lowest value. We just maybe have in mind that the sensor E begins to see particles up to 0.5, whereas the other ones see particles beginning to 0.3 micrometer. Also, we can see a difference in the delay for the peak of pollutants. So all are those differences due to the sampling of the data, the averaging of the values, or the sensitivity of the sensor, maybe all of them. The sensor response to tobacco smoke is something different. If you remember, just below, the E sensor gives the lowest value. Here, the E sensor gives the highest value. In fact, tobacco smoke is mainly composed by fine particles. And the order also of magnitudes for the response of all sensors is different because the size distribution is not the same. And what we can see here is, for example, if you have the orange value, you have here the PM 2.5 and PM 10, so you have a difference regarding the size taken into account. And the B2 and the E sensors give highest value than the PM 10. So I think it's something that has been already showed just before, that the magnitude is different and also is going higher than PM10 values. The sensor response to talcum powder. This experimentation was not easy to proceed because the talcum powder is much more heavier and it deposits more quickly. Anyway, the order of magnitude is still not the same, and we can see that some sensors react very little to this talcum dispersion. Hopefully, there's not often talcum powder in our rooms in indoor air. Here you can see on this E sensor that the peak is really delayed. You have a time lag, and yes, we can guess that it is due to the average of the values. So those are some differences with injection of pollutant with quite a high level of concentration, and we wanted to know what is there any difference when there's quite no pollutant, like in indoor air environment. Usually you don't have incense smoke just behind your sensor, and in fact, even when there's no particle generation close to the sensors, there's still many difference in the value that are given by the sensors. So those are the results for 3 kind of sensors, 2 products by each. And we see that this basic level is either 5, 15, or 30 microgram per meg cube. So it might be a problem if people want to take values as quantities and not as qualities. Now for VOC measurement, so it's a complex gas. There's only 3 sensors that were available, and I named them sensor G, H, and I. There's still no many information on the quality of measurement for those values. Most of them are measured using MOS technology. So what is given on the technical data from the manufacturer is the type of gas that can be measured. So formaldehyde, isobutane, hydrogen gas, ethanol, toluene, and ammonia, benzene, and they just give the range or say that it's given in ppb. And the sensor E, the problem is that it gives values in a microgram per metr cube. And we wanted to make the transposition, microgram per metr cube into ppb, but for that we need the gas density, and as VOC is a complex gas, we don't know exactly the composition, so we are not able to give the density of this complex gas. And in fact, it varies for each type of pollutant generation. So we will focus on G and H sensors. So here is the sensor response. Here is the sensor response to VOCs. So first of all, we generated tobacco smoke in our testing rooms, and in the morning and in the afternoon, after cleaning the room, we have we have put cleaning wipes in the room and close to the comfort fan, and then we just had to wait. What we can see directly is that the values differ between those sensors, G and H. Two products gives almost same results, even if as for G, it's not really exactly the same value, but for the H, the two products gives almost the same value. But what we can say is that the magnitude of response is really not the same regarding the type of pollutant. For example, the sensor H almost do not have any response to these cleaning wipes, whereas it has a big response for tobacco smoke. And the sensor G reacts more for cleaning wipes than for tobacco smoke values. And for, I would say, low level of pollutants, so it was after the cleaning of the room and after one night in the CETIAT, the basic level of those sensors were either 130 or 600 ppb. So there's a disparity of this low level value even with no VOC generation. So the conclusion of our study regarding the measurement results is that there is high disparity between the sensors. We have seen that we guess that there's a main impact from the data sampling and the averaging. It induces a time lag, and it lowers the peak value on the results. There's also an impact of the pollutant composition, the size distribution, or the matrix of gas used. If it's instant, tobacco, talc, or cleaning wipes. And the sensor response are different, so it's the sensor are not the same sensitivity. It's sure now, and we have seen that there's very few information available when we want to buy those sensors. Few information on sensitivity or selectivity of the sensors, on the data processing, and also on the ambient condition influence. Now, if our conclusion regarding the assessment of IAQ sensors, our position is to say that we need to characterize the generated pollutant, its nature, its composition, size distribution, type of gas used, and also its properties, density. And there's a need to put into force periodic calibration of the sensors using complex pollutants and not only one gas. We have seen many manufacturers for VOC sensor that said, oh, okay, I'm calibrated with one gas, so it should be okay. And we can guess that it's not enough. And I think that is in the standard ISO 16000 part 29 for VOC's sensors. They say that you have to use a matrix of gases. And for particles, we are sure that we need to assess each sensor regarding different size distributions also. And the question is how to do for those on-site sensors. Do we need, or we will be able to calibrate them, as it is a quite a heavy calibration procedure. And now for the last conclusion for this webinar, what is the use for these low-cost sensors of particulate matter and VOCs? So to our point of view in CETIAT, for individual use, it's okay. And it's for information purpose only, and the end user can be aware of its own indoor air quality and on the impact of its own activity on its indoor air qualities. Many of those sensors give tips to say, oh, can you improve your indoor air quality? But for demand control ventilation use, we know that some sensors are connected to EFTT protocols, and it should be easy to say, well, I will connect my ventilation system to this data. We would be aware that we need to improve the reliability to this to data, reliability of connection, and also the durability of the response. We have no value for the moment on the durability, and maybe the need to have periodic calibration for these sensors. So, thank you for your attention.